All right, Alex, go ahead and take it away.
Hey folks, I'm Alex Morgan. For those who don't know me, research scientist here at PSI. I'm giving a talk at William and Mary down the road from where I live next week, and so I figured if I gave a synopsis here at PSI, it would force me to make the talk more than a day in advance, and I wouldn't be so stressed out the hours leading up as I threw a PowerPoint together. Okay, so if you were to open the New York Times in 1911, this is what you'd see. So people have been really interested in what's going on the surface of Mars for a pretty long time, and particularly what water might be doing on the surface of Mars, because that has obvious implications to life. And so this was really exciting at the beginning of the 20th century. But then, as everyone who I'm on this call, oh, and I should just note this William and Mary talk, it's to a general geology department with no planetary scientists. So there might be some stuff in here that's a bit basic or things that typical PSI staff know a lot about. But yeah, when Mariner 4 arrived at Mars, it looked very moon-like. There were no canals, there were no Martians, in general, no surface water. It's a very heavily cratered surface, indicating that there's very little erosion. Thin atmosphere, that's a typo. Very cold and low surface pressure. But fortunately, we didn't stop going to Mars at this point in time. 40 years later, Mars Odyssey, when Viking in between, Mars Odyssey returned these very nice global 100-meter per pixel images from the Themis instrument. And it's really, this is of the same area, the image on the left and the right. It's very apparent that Mars is not so moon-like. There are some craters that are very degraded. Some have ramparts. That's this fluidized material that moves out of the away from the crater, suggesting impact into ice or water. And there are these extensive valley systems and Paleolithic basins indicating that in Mars's past, it was pretty different from the Earth, or pretty different from how it is today. So here's a fairly typical region of the Martian highlands. A couple of things that's one of the immediate things that sticks out is the valley networks, which are highlighted black here. And these valley networks, you can think of them as somewhat analogous to Earth river valleys, but they're not truly dendritic. They have poorly integrated watersheds and low drainage densities. And they also have non-concave longitudinal profiles. And I know that's a lot of geomorphology words, so I'll explain what that means. So if we're talking about a river valley on Earth, they're usually dendritic. And what this means is they're like tree branches or tree roots. And often what that means is you have one large branch and then it will split into two branches of about equal size. So an example would be if you're in Harper's Ferry in West Virginia, where the Shenandoah River meets the Potomac River. The Potomac River is bigger. It has a discharge a little less than double of the Shenandoah River, but they're not that far different. They're roughly similar. And this is different from on Mars, where you'll see on the image on the left, there's really one main valley stem and then some, or typically there's like one main valley stem and then some smaller tributaries coming in. And you'll also notice that most of the surface does not have rivers and does not appear to be incised fluvially. That's very different on the Earth from where almost anywhere you go, you'll see some like even dry areas, you'll see the impacts of fluvial erosion. And so together, these observations have been interpreted to indicate that valley networks never fully integrated the landscape. So maybe these were active just for a short period of time. And we'd really like to be able to investigate these fluvial systems in situ with a rover, which unfortunately has not been done for valley networks yet. Valley networks have only been studied with orbital data, but Curiosity and Perseverance have both observed conglomerates with rounded rocks in Jezero and Gale craters. Jezero top, Curiosity or Gale at the bottom. And this is cool because these rounded rocks are a sign of fluvial transport. So as rocks move downstream, they start out big and angular, and then they get more rounded. If you've ever been to the headwaters of a river up in the mountains, there's lots of big angular boulders. And as you move downstream, you start seeing lots of those rocks that are nice to skip across flat water. And we can infer the transport history of these rounded rocks. So basically, you have a rock gets less massive as it moves downstream. And so that's a combination of both abrasion, which is the more The less regular parts of the rock are going to be the parts that get smacked into other rocks as it moves downstream. So those are going to erode downward. That's abrasion. And then sorting is that the smaller rocks are able to transport further than the bigger rocks. And so this is kind of tangential to the main thrust of the talk, but I just want to give a plug to my PhD student up at Dartmouth, Emma Rogers. So she's been looking at how rocks of different lithologies round as they move downstream, partially with field work, but also using this rotating drum in the lab. And what she's found is that basalt rounds significantly faster than granite or limestone, basalt being the dominant lithology that's on the Martian surface. And she's using this to answer a few questions like how far were these pebbles transported? Can we identify where in the watershed were they sourced? And then can we figure out how long did fluvial transport last? And this last question, how long did fluvial transport last, brings us back to the valley networks. It's like, how long were these active for? So the way that people have typically done this in the past is you measure some properties of the valley. So this is a cross section of the valley, either looking upstream or downstream. You measure the eroded volume, so the amount of material that's been eroded away as the channel is incised into the surface, and some properties like slope and width. You then make some assumptions to estimate the amount of water that was flowing through the system. You have to make a lot of assumptions like the grain size of material, the bedrock erodibility, the sediment concentration. So it's like a thick debris flow, or was it like a clear water flow? Flow rheology. There's lots of assumptions, but generally this gives you a reasonably order of magnitude approximation of the amount of water moving through the system and the amount of sediment moving through the system. And then you come up with an erosion time, which is just the volume of eroded material divided by the sediment transport rate. But this is the erosion time if low conditions were constant, which is unrealistic. Most rivers do most of their work when there's a big storm or a big flood. Most of the time, rocks are not constantly moving downstream. And so what folks do is they multiply it by this intermittency factor, which is the fraction of time in which the bankful flow, which is what's been calculated here, would accomplish the same amount of erosion as the real hydrograph. So the way to think about this is I go to AGU for about a week every couple of years. I've been maybe 7 weeks in the last 10 years. So the intermittency of me at AGU is 0.013, 7 weeks divided by 10 years. But we have no idea what this intermittency value is for Mars. And so for previous workers, some of whom are cited here, they just assume some value like most of the sediment transport would have been occurring either 1, 5, or 10% of the time, which is thought to equate to arid, semi-arid, or humid conditions. And they use this to come up with some time scale, usually on the order of 100,000 to about 10 million years. And so that's the time scale they took to form. Another question is, when did they form? And the way we do that is with impact craters. The concept at its most basic is pretty simple. If impact craters are constantly hitting a surface, if that surface has a lot of erosion, or if something resets the surface like a lava flow, you're going to have impact craters get erased, and then that's going to tell you that the surface is young. So for example, Earth has hardly any craters, so it's a very young surface. The moon has tons of craters, so we know it's an ancient surface. Mars is somewhere in between. It has fewer craters than the moon, and they're also degraded. And so we can date a surface on Mars based at its most basic. If there's more craters, it's going to be older. If there's fewer craters, it's going to be younger. But we can try to make it a bit more quantitative, and this is using models for using both what's called a chronology function and a production function. I don't really get into the details of it in this talk, but the basic idea is that you get absolute ages using radioisotope dates from areas that have been crater dated from lunar samples from the moon, and use that plus the relative impactor fluxes of the moon system versus Mars or any other planetary body you're interested in dating, and you come up with some absolute age. And that gives you a plot like what's on the right. And the way to read this is the crater diameters on the horizontal axis and the number of craters per square kilometers on the vertical axis. So on the 1 million square kilometer Mars surface, if it's 1 billion years old, you'll have 6 1 crater kilometers, or 1 kilometer craters. Okay, and if it's 4 billion years old, there will be 40,000 1 kilometer craters. When you plot these, they typically look like this, and there's this drop off at lower diameter craters because of preferential erosion. Smaller craters are easier to erode than larger craters. And you'll note the 3.5 gigaannum, that's 3.5 billion years ago. And this gets to this point, which everyone here at PSI is well aware of, but for geologists not working in planetary systems, this is incredibly old. So on Earth, I was at the Smithsonian Museum of Natural History, and they talk about deep time. There's the whole deep time exhibit hall, and they're talking about things in the Devonians, 300 million years ago. Yeah, that's cute. But on Mars, we're talking about billions and billions of years ago. So if you look at the geologic time scale of Earth versus Mars, dinosaurs, non-algae land plants are all basically yesterday in terms of Mars geologic history. On Mars, we're dealing with stuff that's so ancient and in such early solar system history. And that's really cool because on Mars, this is when there was valley networks, this is when there were lakes, there might have been an ocean. On Earth, this is when there's some of the earliest known life. It's from about 3.7 billion years ago, or 3.5 billion years ago from a chert in Australia, I think. But the geologic record from this period is mostly erased. It's very rare that you can find rocks from this period in Earth history. And on Mars, you don't just have rocks, but you have entire landscapes that date to this early part of solar system history. And so in a way, we're able to look at the Martian surface that's easily visible from orbit and learn something about what the Earth might have been like during its early history, of which we don't have a record anymore. Okay, so when we date these, though, there's a problem. So valley ages from crater counting vary by hundreds of millions of years. It's not, and that's so vary by hundreds of millions of years. And fluvially infilled craters indicate that individual deposits would have formed over hundreds or millions to tens of millions of years. And this is different from what comes up from that paleoflow reconstruction, where it's about 100,000 to 10 billion years, or the cratering record, where it's about 1 million to 100 billion years. So what's the problem? It's probably this intermittency factor, which we really don't have any good knowledge of what it might have been like on Mars. So we don't really have, there's not really a good reason why rivers would be active 1, 5, or 10% of the time. So on Earth, on the right, these are some plots by Hayden et al. In GRL, where he's looking at the intermittency factor and how it varies as a function of aridity, system grain size, the time scale of the system. And on Earth, it varies really widely, and it's not really correlated with climate. And one big factor in the intermittency is things like storm frequency. And this is affected by a number of processes which are kind of unique to Earth. So like global climate circulation, oceans, which would not apply to Mars. And when we're thinking on Mars over really long, million-year, multi-million-year timescales, we have to start thinking about orbital parameters, essentially Milankovitch cycles, large-scale volcanism, etc. And for a couple of spots on Mars where people have tried to calculate the intermittency, so like in Milne crater here by PSI or Peter Buehler, or Jezero crater on the right, people come up with values that are much lower than what's been assumed for these valley network systems. Okay, so can we better constrain the total time scale over which these valleys were active? So I looked at these 8 valley systems in Nuacas Terra and Western Terra Sevilla. We're going to zoom into Bauschkas Vallis here. This is what it looks like. Let's zoom in a little bit further. So this is it in CTX. And what we can see is that there's valleys that predate the valley network and then valleys that postdate the valley network, which are highlighted in red and blue here. And we could use these to come up with some just absolute bounds. So a maximum, if we date a surface that only uses the pre-valley craters, and then we date the system using post-valley craters, we can come up with some maximum bounds over which the valley network might have been active. So plotting those, somewhere 3.7 to 3.5 billion years, like in that range. Now, granted, these are maximum bounds. It's very possible that this is some surface where it formed the blue craters and then just sat there doing nothing of much interest for a billion, 100 million years or something, and then fluvial activity happened. But I think it's still worthwhile to have these maximum bounds on when or on how long fluvial systems might have been active for, because oftentimes all we're calculating is the minimum time scale over which they could have formed. Okay, so assuming the sediment transport and flow rates previously calculated, this would imply, if they were active over this total time scale, this would imply an intermittency of about 10 to the minus 5. So this is much smaller than that 1, 5 or 10%, but it's similar to those values that were calculated for fan deposits by Buehler and Lepotre. This is lower than Earth intermittency, which maybe should be expected because it's Mars and this is over a pretty long time period. And this would suggest long-term erosion rates. This is, if you look at that time scale and look at the depth of erosion into the surface, of about 0.5 meter per million years. And so this is similar to the modern, or some parts of the modern Atacama Desert, and also Noachian crater degradation, which, that's promising that these are, it's similar to that. So just for the sake of argument, like if maximum valley formation ages are hundreds of millions of years, what does this mean? So work by a colleague, Stucky Deki, has looked at hydrologic balances between lakes and has, excuse me, has found that individual river permitting episodes would have been somewhere between 100 to 10,000 years. And so what this might mean is that there had 100 million years of time scale over which valleys were forming, and it was very episodic. Like there was that's shown in this upper left here. So you had a less than 10 to the 5th year river permitting climate episode where intermittency might have been kind of Earth-like, and then you had a gap where not much was going on. Perhaps these were driven by Milankovitch-like cycles. So Mars undergoes these big shifts in its obliquity. When that happens, it's going to change the weather patterns and climate on Mars. And so an important thing to note is that we should expect, if this is happening, we should expect to see impact craters disrupt flow paths, because unlike on Earth, on Mars, topography is created instantaneously. So on Earth, you have a mountain, it's building upward. The entire time it's building, it's being eroded into. And so you have this equilibrium between erosion and mountain building. On Mars or the Moon or most planets, that's not the case. So you have topography is created basically instantaneously by the impact, whereas the fluvial erosion is occurring roughly constantly, other than some intermittency or periodicity. And and we see evidence of this on Mars. So like this is an example here of where there was an initial flow path that went along the dashed and dotted line, and then crater A formed, and its ejecta blocked the flow path. The flow is then redirected along into crater B, then outflowed. This is another example. Same thing, or mostly the same thing. Crater A formed, it blocked the flow path, which caused, crater A formed, which blocked the flow path and caused flow to divert up along Valley 2. And these are just 2 examples, and there's many others. And multiple 50-kilometer craters imply tens of millions of years of fluvial activity, because you have to have a pretty long period to form, pretty long period over which these large impacts happened. And with this competition between fluvial erosion and impact cratering, these should create lakes, because this is going to be creating a lot of dams that are blocking flow paths. And indeed, we see lots of lakes on Mars. So work by Tim Gouge and others have identified about 400 paleolake basins across the Martian surface. And most of these are hydrologically open, meaning they're like the blue one at the lower right, where there's an inflow and then there's an outflow. And a lot of these outflows are perched. So the lake would have had to have been at some elevation or at some depth to be able to flow out. And some past work has suggested that these outflows were formed rapidly from catastrophic lake breach flooding. How do we know that? So you can test by comparing the eroded outlet volume and the drained amount of water. So here's a crater on the slope surface. There's some amount of water that's coming in. It fills up the crater, and there's some pre-breach lake level. And then it erodes, so the part in gray is not there anymore. And you can compare the drained volume in light blue with the volume of the eroded outlet. And these have this pretty close correlation between these 2 things. And so that's not what you would expect if this was erosion over. So say an alternative hypothesis could be you have an impact crater and you have a river channel that's headward eroding. So it's eroding into bedrock as it moves its way, as its head moves upstream. And eventually it might intersect with this crater and form a breach. But in that case, you wouldn't expect there to be a correlation between the drained volume and the outlet volume. Another piece of evidence is in some craters, like here in Jezero, you see what looks like flow convergence. So to the left of the blue arrow, and this would be areas where the flow is being forced into this narrow outlet at high discharge. And this is really not so different from what we see in times on Earth when the climate is out of sync with the topography. So, I mentioned on Earth, mountain building occurs in conjunction in this sort of equilibrium with erosion. But every now and then, the conditions really change. And so if you think on Earth during the late Pleistocene, when there were ice sheets covering most of Canada, there were lakes across much of the now arid Southwest. And this was an amount of water in those areas that the landscape had not evolved to have. I mean, this evolved is kind of the wrong word there, but and so what happens is you have lake breaches, and so the quintessential example is the Bonneville Flood, which flowed out along the modern day Columbia River. Okay, so our question was, how much did this lake breach flooding contribute to fluvial erosion on early Mars? And so we used existing maps of valley networks and paleolake basins, and we just identified the valleys as either valley networks or paleolake outlets. And then we just calculated the cumulative eroded volume of each valley class. So this is the distribution of what are lake outlets, possible lake outlets, and other valleys. We tried to be pretty conservative. So here's an example. The blue is what counts as lake outlet. And if a lake outlet intersects with a valley of equal or greater width, then it stops being a lake outlet. So we're being conservative with the amount of lake outlet erosion. So then we automate, so then we have to get the amount of volume, the amount of eroded volume. And so we do this with this automated method, this progressive black hat transformation. Think about like a black top hat, like what Abraham Lincoln would wear, put it upside down, and think of like many of those at different sizes. And so this algorithm grows outward and kind of tries to find the best size top hat that fits within that valley. And the brim of the hat would be the valley shoulders. And we use those valley shoulders. So it's like the top hat that would fit best in the valley shoulders. So we use this valley shoulders as a proxy for the pre-incision surface. I think there's an animation. Yeah, okay. So this is sort of how it works. It like builds its way outward and created bigger and bigger top hats until it kind of reaches equilibrium where it stops growing. Then we go through, then there's a flow routing algorithm that connects the different sectors that are connected. And then we go through and do a manual fix to make sure that things like impact craters aren't included, like this one towards the bottom that fills up. We erase that one out. Yeah, we go through and erase the bad craters by hand. And then we just use the MOLA topography to figure out the amount of depth that's included in each of these areas and use that to get the volume. Okay, and so the result is a pie chart. And so, this is kind of a cool project because we used data that's 15 years old, I think, or older. It's MOLA data and Themis data. And the main result is a pie chart with two things, and it's a Nature paper. So that's always cool. And what we find is that paleolake outlets, despite accounting, they're only 3% by length of valley systems on Mars in general, but they account for 24% of the eroded volume. So they have a really outsized role in shaping the topography of the Martian surface. The reason they have such a higher volume contribution is they're a lot deeper than valley networks. And what's important to note is that these deep valley systems, the deep paleolake outlets, would have affected the topography of many other valley network systems. So in this case here, the we have valleys A, B, and C. These are not paleolake outlets. They're just flowing into a paleolake outlet, but their base level, as shown in this long profile at the bottom, is going to be really steep at the bottom because they're flowing into this really deep outlet. And that's going to affect the slope of the overall system. And so any of these adjacent fluvial features would respond as a result of these lake outlet decisions. And because these are distributed across the Martian surface, this would affect the form of many Martian valley systems. So an example is here where there's, only a couple of or three lake outlets, but lots of these other valleys would have all had their morphology affected by the draining of the lake and by the formation of the lake outlet. And this may explain why valley networks differ from Earth. So why they have these non-concave long profiles, because they're all just formed in one go, why there's low drainage density, why they're not dendritic. And yeah, this 3% length versus 24% volume, should this be surprising? Probably not, because as I was describing earlier, Mars's surface was not hydrologically integrated. You had a surface that was formed with a topography that was largely impact craters. There was not flow paths for water to be able to move. And so when water was available on the system, that water wants to go downhill, it's going to breach crater rims, and it's going to find a path down to its terminal destination. And this is true on Earth too. So on Earth, lake breach floods are suggested as important for integrating landscapes of disconnected basins. So for example, like the Basin Range province in the Southwest. And the prominence of these on Mars suggests that these systems were immature and that the landscape was never fully integrated. And so, yeah, the Basin Range in Nevada might be a useful analog to Mars in this regard. Yeah, so that's it. And so just the main takeaways. So during the Noachian, precipitation-driven erosion competed with ongoing impact cratering. Conditions permitting fluvial erosion were intermittent and potentially spanned hundreds of millions of years. And the catastrophic lake breach flooding was a major contributor to erosion on early Mars. And thank you, and I'd be happy to take any questions or take any feedback.
Alex, I have a question. Can you hear me? It's David. Yeah. Thanks for that. Nice talk. I was curious when you kind of take apart a drainage basin and look at the craters that predate and postdate and extract those ages. Have you also looked at the age constraints you get from the crater floors that predate the erosion?
So not for these, because a lot of craters just aren't that big, the ones that I used. And so I don't know if they'd be large enough. One thing that Sam Bell at PSI and I've chatted, and I don't think we're making it in this cycle, but for the next S Cube, is looking in some of these examples where we see impact craters that have intersected. So like these ones like crater A, these ones are big enough to date for sure. And so in these cases, like it wouldn't be before the primary flow path on one, but like this happened before two. And so this one we could definitely date, and then that's providing firmer constraints on not the beginning of fluvial activity, but at some point during fluvial activity. And then we get some constraint at the end of fluvial activity from this guy.
Thanks.
All right. Does anybody have any last questions for Alex? Awesome. Well, thank you so much, Alex, for giving this talk, and looking forward to the next one.
Great, thanks everyone.
Yeah, and good luck on your talk tomorrow.
Yeah, next week.
Next week, sorry. Yeah, next week.
Thank
All right,
you.
thanks everyone.